Hello everyone, welcome to our channel Code with Sunny, and today in this video we will be discussing the hard problem of LeetCode. Problem name is word ladder. Its index is 127. Right, okay. So before moving on, let me just talk about the prerequisites required to solve this problem. It is nothing but a breadth first search, like if you have heard in the graph theory BFS term, like we are going to use the same approach. Okay, and also like after doing this problem I would just strictly recommend you guys that you are going to hover over the section called similar questions, and here you will find the word ladder second, like the second version of this problem, which is quite much interesting. Like yeah, if you look out the same tab for me, it you will find that yes, I have also solved this problem, and this is in my favorite list because yes, we are going to learn something new. Okay, so I would recommend you guys to do this problem also, and if you are stuck upon that, like word ladder, then you are watching the correct video, that is the current video. And if you guys have stuck on the second problem, like word ladder second, you can see the same video is already present over my channel, like it was published on 24th of July 2021. Yes, if you are going to face the doubts, you are going to look out for the same video. Okay, then like everything will be clear. So without wasting our time, let's understand what this problem is going to ask and how we can solve this one efficiently. So a transformation sequence from word begin word, so there will be a starting word and there will be the ending word using a dictionary word list. So there will be a dictionary that will be given to us that will specify there are certain list of words that we can have during any transformation sequence. So a transformation sequence from word begin word to the end word using a dictionary word list is a sequence of words begin word to s1 s2 and it goes up to sk such that every adjacent pair of words differ by a single letter. Okay, so yeah, I would explain it with the help of examples. So for now, let's complete that. Every si for I belongs to 1 to k is in the word list. Note that begin word does not need to be in the word list, and the last word of this transformation sequence must match with the end word, because you need to reach to the end word, right? So it must match with the end word. Given two words, begin word and the end word, you can consider this as the source. Like if you are like familiar with the graph theory terms, you can understand that you are at the root node, like begin word is a root, and then you need to reach out the destination node, like from a source node to a destination node, and that destination node will be signifying, like will be signified by this term end word, that will be a string, right? And a dictionary of word list would be given to us, like it will specify the words that are going to be visited during the path from this source node to the destination node, and we have to return the number of words in the shortest transformation sequence from begin word to the end word, or 0 if no such sequence exists. Okay, so if you are familiar with the breadth first search, the like it will be clicked to your mind at the very instance when you are going to read this problem, and the reason is you need to find the shortest transformation sequence, and whenever we need to find some shortest path, and the path from a current node to the next node doesn't contain any weight, you are going to use a queue based approach, which is nothing but the breadth first search approach. And with the help of that, we are going to get a shortest transformation sequence from a source node to a destination node. And the only difference is, like we have a source node which is signifying a string, which is nothing but a begin word, and there is an end word also, that is nothing but a like destination node containing a string. And all the nodes which lie on the path from source node to the destination node is going to satisfy this condition. Like each node containing the string will be present in the word list, as well as the adjacent node must differ by a single letter. Okay, so let's try to understand this with the help of examples. So let's begin. So let me just fill out the examples first. Like we have a begin word, let's say I have begin word as hit. Okay, and all the rest of the words are, let me write down over here hot and dot, and the rest of the words are dog, as well as lot, log, and so LOT, LOG, and COG. I don't know, the words diff sounds very awkward. Okay, no need to worry about. And this is actually the begin word. Let me write down clearly begin word. And we have a end word also, where we have to reach end word, and end word is nothing but COG. Okay, so we need to find a shortest transformation sequence such that we start with this hit and we will reach with the word COG, and all the letters that lie, like all the strings that lie in the path from hit to COG, have their entries in this dictionary which contain a strings, all the strings. Like suppose we want to move from hit to hot. Can we move? Yes, we can move, because hot string is present in this dictionary, and the number of characters which differ in the hit and hot string at their positions is exactly 1. So if you look at the conditions, it is nothing but every adjacent pair of words differ by a single letter. Like if you look out, H and H is matching, I and O is not matching, so the one character that is not exactly matching is now become 1, their frequency becomes 1. And T and T is matching, so number of characters which are differing is exactly 1. And this hot string is present in the dictionary, so we can go from hit to hot. Okay, so yeah, so we need to find a shortest transformation sequence such that all these criteria will be satisfied, and the number of words from source to destination should be like minimum, like we have some integer, and that integer should be minimized. So we are going to use a breadth first search. Let me write down BFS. So what BFS is going to do is to perform a level order traversal. So this is at the level equal to 1. So this is at level equal to 1. So let me just move out to the level equal to 2. So all the nodes, all the strings which are at the level equal to 2 must be differing with the string hit, like must be differing by exactly 1 character, right? So we can move from hit to, let's check out, can we move from hit to hot? Yes, we can move. So I will write down over here, can we move from hit to dot? No, we cannot move. You can see D and H is not matching, and O and I is not matching, so the number of characters differing at their positions is exactly 2, so we cannot move. So dog is also not good, like we cannot move from hit to dog. Let's check out LOT. You can see number of characters which are not matching with this hit and lot is exactly 2, so we cannot move from hit to lot. So let's check out LOG. Can we move from can we move from hit to LOG? No, we cannot move, because L and H are not matching, I and O are not matching, and T and G are not matching. So the number of characters differing is 3. So we cannot move. And can we move from hit to COG? No, we cannot move. So it means that there is exactly 1 string through which we can move, that is hit to hot. Okay, so this is at level equal to 2. So let's now check it out. Like yes, you need to also keep track that the strings that are visited, so you will cut down this one, hot is being used. Now from hot, can you check out which strings we can move, like for level equal to 3? So you will check it out, can we move to dot? Yes, the only characters that differ is like the first one, H and D, and yes, the frequency is 1, number of characters differing is 1. So we can move from hot to so that should be a dot, right? So dot. Okay, so and the next one is like, can we move from hot to dog? Let's check it out. No, we cannot move, number of characters is exactly 2. You can check it out like that also, hot and dog. T and G are not matching, so frequency becomes 1. O and O matching, H and D not matching, so frequency becomes 2. So when frequency becomes 1, that is the number of characters not matching, then we can move. So yeah, you need to also extract this one, like dot is being utilized, that is being visited. Okay, so let's check out LOT. Yes, we can move, because H and L are not matching and rest of the characters are matching at their respective positions. So we will move to LOT. And yes, we will cut it out because this is visited. So can we move to LOG? No, we cannot move. Can we move to COG from hot? No, we cannot move. So only the strings that are at level equal to 3 are this one, considering hit as the source node. Okay, So let's try to move to other ones. Can we move from dot to dog? Yes, we can move, because the only characters that differed is G, that is the third one. Can we move from dot to log? No, we cannot move. Can we move from dot to cog? No, we cannot move. Can we move from lot? Yeah, you need to extract the dog also, like it is no longer being used. So yeah, and you need to check out lot and log. Yes, you can move to log, because the differing character count is only one. Can we move to cog? lot, and no, you cannot move. So now the last thing that we are going to do is, like, this is for level equal to 4, and let's check out for level equal to 5. Can we move from dog to cog? Yeah, we can move. So I will write down cog. Okay, and there exists also, like, yeah, we can move from log to cog also. Like there will be a, like, this type. Yeah, you can make, but you need to find a shortest transformation sequence, rather than, like, we are not trying to find out the path. We need to try to find out the value, like shortest transformation sequence, like the level. Okay, so we are not interested in paths. So as soon as we reach the value cog, we will just eliminate it from our dictionary. So you can see the length of the path is what? You can see one word, two word, three word, 4 word, and 5 word. So there exists exactly 5 words. So you can see the output is 5. The one of the shortest transformation sequences: hit, hot, dot, hit, hot, dot, and you can see dog and cog. Dog and cog. Note that it is talking about one of the shortest transformation sequence. So the other transformation sequence is going to be hit, hot, lot, log, and cog then. Okay, so you can see the number of nodes in the path is going to be 5, and this is going to be completely dominated by breadth first search traversal. We can find that easily. Okay, so yeah, so let's head over to the code and understand how we can implement that efficiently. Also, I need to explain some optimization approach we are going to follow up in that coding part. So yeah, you can see I have done this problem on 3rd of February, and yeah, I need to do that again. Yeah, I was like, it was pretty much obvious for me that yes, I'm going to do the same problem again. Yeah, you can see I've written a very much clean code, so you're not going to find any difficulties in understanding this. So yeah, we need to use a breadth first search, and the very key idea is we need to use a queue of pairs, and a pair is going to be like, first element will be the node, and second will be like their level. Okay, so first I will push out the begin word. Okay, and its level is will be 1, and also we need to maintain a visited set is nothing but a set of nodes which are already visited. But here you can see my words, you can see this is actually words, will always maintain the set of words from our word list which is still not yet visited, and when we visit that node, visit that string, we will try to eliminate that string from the words. So our words, which is nothing but an unordered set of strings, will always contain those strings which are still not yet visited. Okay, so keep all unique words which aren't visited yet. Okay, and yes, you are going to push out in the queue, so you will erase the entry of begin word if it exists. Okay, now the thing is, like, you need to do a breadth first search. We will extract out the node, extract out its level. You can see string v and int level, and if this v, string v, is exactly matching with the our target node, target string, which is nothing but an int word, then we are done. We will return the level, which is nothing but a length, like total number of nodes occurring in its path. Okay, now the very important thing is, like, how do we search for the next level nodes? Now the key idea is, like, you can focus over the description. It says that yes, every adjacent pair of words differ by a single letter. Now when it differs by a single letter, what we are going to do is, like, we will check out every position of our current string. Let's say the current string is of length 5, so we will iterate for every position starting from 0 to 4 if we are considering a 0 based indexing, and for every position you can see I0 to v dot size, which is the current string dot size, and for every position we will try to put out the character, right? We can also do like this. We can also like we will check out the hit string, and we will traverse through all the set of dictionary of strings, and we will check it out whether this hit is matching, like whether this hit string is satisfying the criteria that the number of characters that is going to differ is only one or not. We can do that, but yes, there is some more efficient way to do that. And the thing is, we will try to put out the character at every position, and the character is going to be like any 26 lowercase characters. Okay, so consider that I am fixing I, which is some position of the current string. Then we will try to put out every character at this position. It will start with A and end with Z. Okay, and if when we are trying to put out this character, we will just search on this words we have. You can see another set of string of words which will actually storing the unvisited strings. So we will check it out if after putting this current character at this current position, whether this new string is going to be present in our words or not. Like in more formal way, it will search whether this string, which is actually the new string and it is differing by exactly one character, is still yet not visited or not, and this string must be occurring in the word list. Word list is nothing but a vector of string that is being given as an input, and we have already mapped all the strings which are present in word list to our another set of string of words. So whenever we will change a particular character, and like we are placing out a new character, we will search that whether this string is in our data or not, as well as it is still not yet visited. Then we will use that string, that is the new string, and what we are going to do is we will push out in the queue, and we will erase that entry from the another set of strings, which is like set of unvisited strings. We will erase that because this string is visited now. Okay, and doing these operations, we will like whenever we will find out the destination node destination string, we are done. We will return the level, and if you're not going to find, return 0 in that case. Okay, now let's talk about the complexity of this code. Okay, so you can see the queue we are going to use, it will use out every word. Like in the worst case, it will try to take out every word present in this word list, right? So let's say the length of this word list is going to be n. So we have O of n, and for every word we are iterating to the its length. You can see its length. So let's call m as its length. So O of n into m, and for every position you are going to search for 26 characters. So O of n into m into 26, but you can see extra m is coming out over here, right? So it comes out like this one. Like whenever you're searching for words dot count str, it is actually doing an O of 1 operation, right? But when you're searching for, like when you're matching the exact string, it will match it from the starting position to the end position. Okay, searching in the set takes O of 1 time, but matching the string takes O of m time. Okay, so it will be like O of nm squared into 26, and the space complexity would be like it will be not be O of m, it will be like O of n. N is nothing but a vector of string of word list. Okay, so let me correct it down over here. It is actually O of n, yeah. So this will be our time space complexity, and time complexity O of nm square into 26. Okay, yeah. So if you guys have still any doubts, do let me know in the comment section of the video. And yes, thank you for watching this video, and don't forget to subscribe.